In this example, we will investigate our final application of the definite integral, using it to calculate work. So the starting point for this conversation is to remind you, if you have a constant force, the key word here being constant, and it moves an object a distance d in a straight line, then the work done, and this is probably the formula we've all encountered in the past, is force times distance. So the big question then, what if the force is not constant? How much work is done by the force in moving an object from x equals a to x equals b? Well, I'm going to think about this in the following way. So we're thinking about moving an object along the x-axis from x equals a to x equals b. And because the force is not constant, it's represented by a function. What we have to do is instead think about this from a definite integral perspective. We say, okay, let's take this interval, like we've done many times now, break it up into a bunch of these equally spaced subintervals, and approximate the work on each of these intervals. So if we once again have the ith subinterval, so x sub I minus 1, x sub I might want to know what is an approximation to the work on this ith subinterval. Well, what we can do is say that what you're doing is you're applying a force and a distance. The force isn't constant, so what we're going to do is approximate it by using the force at the right endpoint. So we're going to say an approximation to the force on this interval is simply the force at the right-hand endpoint, f of x sub I. And then we just multiply it by the distance that we have moved, delta x. So we take this quantity, we add it up over all the subintervals, and then we take a limit as n goes to infinity, and that's going to give us a definite integral. So in this case, when it's a non-constant force, the work is going to be the definite integral from a to b of the force function. And this will calculate how much force is done over the interval from a to b, or how much work is done by that force in moving the object from a to b. So this is the key formula, but hopefully some fairly good intuition here in terms of where it comes from. So the first type of example we're going to apply work to is going to be problems involving Hooke's law. So let me remind you, this is something that you may or may not have seen, but if you have seen the reminder, the force F of x necessary to keep a spring stretched, or it could be compressed, x units beyond its natural length, is given by f of x equals 10x, kx, where k is the spring constant. And here I'm kind of just, thinking of a simple picture. We're starting off at x equals 0. Well, we're starting off, we have an axis here, and we have a spring. And you have kind of the natural length of the spring. So this is unstretched. And we will think of where it stops here in its unstretched position as being x equals 0. Then what we're going to do is think about, let's stretch the spring out. So you stretch the spring out a bit. So when you stretch it out, you have x equals 0, and it finishes over here at some value of x. And what Hooke's law is telling us is that the force that is necessary to keep this spring stretched is given by k times the amount of stretch, x. So we're really thinking here x is representing the amount that needs to be stretched. So this k is something that we call the spring constant. It's a positive number, and it is something that is intrinsic to the spring. And what I mean by that is that given a spring, there is exactly one spring constant associated with it. So no matter how much you stretch or compress, that spring constant is always going to remain the same. So let's see the type of problems that can be involved with using Hooke's law. So a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. So how much work is done in stretching the spring from 15 centimeters to 18 centimeters? Now, before I get too carried away with this problem, I just want to take a moment and think about units. So when we have force measured in newtons, that means that distance is going to be measured in meters, and work is going to be measured in joules. Additionally, if you had force measured in pounds, so the first case is the metric system, newtons, meters, joules. Then the imperial system, you have pounds, distance is measured in feet, and work is measured in foot-pounds. So in the problem that we're given here, we need to be very careful. Because we have newtons, we know that all of our distances must be measured in meters. So the 15, 15, 18, 10, we need to think of those in terms of meters and not centimeters. So let's go ahead and think about what Hooke's law tells us. So 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to 15 centimeters. So we're thinking of 10 centimeters as corresponding to x equals 0. So that's kind of our starting point. So x equals 0 is 10 centimeters, and 10 centimeters is 0.1 meters. And then we're stretching this out to 15 centimeters, so that's going to be 0.15 meters. To go from 0.1 to 0.15, this is going to be x equals 0.05 meters. So Hooke's law tells us that f of x, or in this case f of 0.05, is 40, which equals k times x. So k is equal to 40 over 0.05. So we have 40 over 5, and then we need to move that decimal place 2 to the right. So 800 is equal to our spring constant k. Now that was an important thing, was calculating that spring constant k. So we now know that our force function in this situation is simply 800x. So what we would like to do is calculate the work that is done in stretching the spring from 15 to 18. So to convert that to a statement, we want the work done by the force, 800x, going from 15 centimeters to 18 centimeters. So remember we said a moment ago that x equals 0 corresponds to 10 centimeters or 0.1 meters. So 15 centimeters corresponds to x equals 0.05. To 18 centimeters, which corresponds to x equals 0.08. And for the first few examples you investigate, the two things to be very careful of are units, because if we didn't get those units correct, our spring constant would have been way off. And also, what x values these numbers correspond to. So x equals 0 is the unstretched spring, the end of it. So if you stretch it 0.05 meters, it goes to 0.115 meters. So 15 centimeters is x equals 0.05. 18 centimeters is x equals 0.08. So the work done is the definite integral from 0.05 to 0.08 of our force. So the antiderivative of 800x is 800 over 2x squared. And we evaluate from 0.05 to 0.08. And when you plug this in and simplify, you get back 1.56. And let me know, what are the units here? Since we're working in the metric system, newtons, meters, work is measured in joules. So 1.56, and I'll just put a J for joules. So another similar example. The natural length of a spring is 0.2 meters. And it takes a force of 12 newtons to keep it extended 0.04 meters. So the 0.04 meters is how much it's been stretched. So extend it 0.04. That's telling us an x value. Find the work done in stretching the spring from its natural length. So its natural length is 0.2 meters to a length of 0.3 meters. So 0.2 meters is going to correspond to its natural length, so x equals 0. And if we stretch it from 0.2 to 0.3, that's going to correspond to x equals 0.1. We've stretched it 0.1 meters. So the first thing we have to do is, once again, solve for that spring constant. So we know 12 is the work done to keep it extended 0.04 meters. So it's F of 0.04, which is equal to K times 0.04. So our spring constant K is 12 divided by 0.04. So 12 divided by 4 is 3. Move that decimal 2 to the right. 300 is equal to K. So now, putting it together, the work done to go from 0.2 meters, its natural length, to 0.3 meters. So that would be x going from 0 to 0.1 of our force. So the force is 300 times x. So the antiderivative of 300x is 300 halves x squared, so 150 x squared, from 1 to 0. We plug in 1, we put a minus sign, that's a 0 to 0.1. We plug in 0.1, we put a minus sign, we plug in 0. So 150 times 0.1 squared minus 0 squared. So that's going to be 150 times 1 over 100, which is 1.5. And once again, the units here, because we're dealing with meters and newtons, is going to be joules.